Okay, so we're going to look at a bit more of conservation of momentum. This is the part two. The part one you would have done previously. It might overlap slightly, but it's probably good to have a little bit of revision as well. So with that in mind, just to remind yourself, pause the video now and see if you can answer that question before I give you the answer. So in this case, our formula for conservation of momentum, well, probably we know what it actually means. That is to say that the total momentum is conserved. But how do I express it accurately as a formula? We tend to do it in terms of just two objects. Let's say object 1 and object 2. And then we would say mass of object 1 times its initial speed plus mass of object 2 times the initial speed of object 2 is going to be the same as that where the u's have been replaced with these indicating final speed. Okay, where initial and final are obviously relative terms, it just means that one occurred before the other. And technically speaking, the full formula would involve sigmas, and then you'd take into account how many objects you've got. So this is just the formula for two objects, but the formula for any number of objects generalizes from the one for two objects, because if it's the case for any two objects in the world, then you can just pair them up. All the objects in the universe, you can pair them up accordingly, and eventually you've deduced that it must be true for all objects. Okay, so that's it. Probably knew that, but let's just make sure we've got it back in our minds while we now look at the examples and problems that we're looking at today. Okay, so let's look at our first example. Two particles A and B of masses 2 kilograms and 4 kilograms respectively. Let me note that down first. So I want us to make sure we're getting used to a sensible way of notation. So let's call it MA and MB rather than 1 and 2. So MA is 2, MB is 4. They're moving towards each other in opposite directions along the same straight line on a smooth horizontal surface. So in other words, oops, that's not straight. In other words, we've got this sort of situation going on, right? One's going to the right and the other one's going to the left. That's the only way in which things could go towards each other in opposite directions. Before the collision, the speeds of A and B are 3 meters per second and 2 meters per second respectively. Note that it says speeds. After the collision, the direction of motion A is reversed and its speed is 2 meters per second. Find the speed and direction of B after the collision. So it might seem fairly simple, you just use that conservation of momentum formula. But I think this question is worth being careful on, because there's a few unknowns in terms of the direction things are going, and I think it's worth thinking that through to make sure you can then apply it to more advanced questions. So I guess the key thing is, out of these, within this drawing, which one of these is A and which one of these is B? And technically, we don't know. There's not enough information in the question to tell us, and in fact, even when we've answered the question, we still won't know. But we will still be able to answer the question. So if you actually label either one of these A and B, you don't know if it's the correct way around or not. It's an unknowable unknown, effectively. But it doesn't matter. Part of the reason it doesn't matter is, if you think of it this way, let's say I labeled that one A and that one B. In terms of what happens between the two objects, they hit each other, they bounce off. If I just did the mirror image of the situation, then that would be equivalent to having labelled A and B differently, and the outcome would be exactly the same outcome, but the mirror image of the outcome. So it's kind of like a symmetry of the universe kind of thing. So in that sense, we don't need to know which one's A and which one's B. So we just want to be careful with our notation, though. So let's look at that second part of the paragraph and just note down the key info mathematically. So before the collision, the speeds of A and B are 3 meters per second and 2 meters per second respectively. So let's note that down. So the speed of A, that is the magnitude of A, U of A, that's 3. And likewise for B, it's 2. Okay. And then after the collision, the direction of motion of A is reversed and its speed is 2 meters per second. Okay. So what we could do, we could continue with this sort of notation with the mod, or we could just make an assumption. And in this case, I'm actually just going to go with making an assumption. Okay. And that is, let's call the left one A and the right one B. And I suppose the technical way of doing this is we can call this without loss of generality, right? Without loss of generality, more commonly written as WLOG. Let's say A is on the left. Okay, and all that's saying is let's assume something which, if we assume it, will still give us the answer that we want. So let's assume A is on the left. So in that case, I'm going to say UA is equal to 3, and that's because I'm taking right as positive. That in itself is an assumption which, without loss of generality, applies to, right? If I say right is positive or left is positive, it doesn't matter. You just pick one, you'll still get a correct answer, and you just have to interpret it in terms of what you initially assumed. So I'm taking right as positive, UA is 3, in that case then UB must be -2, because it's in the opposite direction. After the collision, motion of A is reversed, speed is 2, so VA must therefore be -2, because it's reversed, so it's minus. And now we just want to find V of B. Okay, and now it becomes fairly simple. We're just going to use the formula, right? We'll do, in this sense then, 2 times 3 plus, let me get my laser pointer out. So we're doing MA times UA, 2 times 3 plus 4 times -2. And we're going to say that's equal to 2 times -2 plus 4 times VB. I won't write the whole thing out, but you'll use the equation that we used in the starter. You'll have entirely numbers, except then VB is left over. See if you can find what VB is. Okay, so again, 2 particles, P and Q. They've got respective masses, and they are connected by a light and extensible string. They're at rest initially, and the string is slack, meaning it's not stretched out. So effectively they're not really connected. It's as if they weren't connected yet, but they could be eventually if the 2 objects go far enough apart and the string does become slack. Now they are actually connected particles. Particle P is projected directly away from Q, so P is going away from Q with some speed while Q stays stationary. Find the common speed of the particles after the string goes taut. So what part A is effectively saying is, here are my 2 objects, they're not connected. One of them goes away from the other, and at some distance they will eventually become connected. So your U case is before being connected, and your V case is after becoming connected. So it's a bit different to a collision, but similar idea. When you've got a collision, U means before the collision, V means after the collision. In this case, U is before connection and V is after connection. It doesn't matter how long the string is or anything like that. It's not really relevant. The point is that you've got this before and after scenario. So again, we're just going to consider conservation of momentum in this case. See if you can beat me to it. We've got MP is 8, M of Q is 2. So without loss of generality, again, I'm going to say, let's say particle P goes to the right. So I'm imagining Q is stationary, and I'm imagining P as going off to the right at a speed of 4 meters per second. And again, I'm going to take right as positive. So then we've got v of p, or I should say u of p equals 4, u of q equals 0. And then the common speed of the particle. So here's the interesting thing. So you'd think, oh, we've got two unknowns, right, which are v of p and v of q. What are they? But actually they have to be the same value. Because if you've got, unlike with collisions, if you have two objects suddenly connected by a string, then as they continue onwards, they're going to be going at the same speed, right? They've almost become one in union with this string. So they're going to be going at the same speed. So it's actually just one unknown, and we could just call it something else, for instance. Maybe we could just call it, well, just a single v without any sort of subscript. So Vp and Vq, they're both the same thing. They're both this v. And then we can do conservation of momentum equation again. So we'll have, I'll write it out this time, 8 times 4 plus 2 times 0 is equal to, and in this case I can just shortcut it. I can just take the total mass times its common speed. So that is 8 plus 4 times v. So it's 12v, right? Which makes sense because it's 8v plus 4v. So we've got 32 equals 12v. Therefore v equals 32 over 12, which is 8 over 3. And first mistake is this should be 10. Oops. And therefore, again, correct method, wrong numbers. That's your job. Check me up on these things. There you go, 3.2. Okay, I rushed it. So be careful, you've got a lot of numbers floating around. Just obviously when you're doing this in real conditions, you want to be careful where your numbers are going. Okay, so 3.2, that's our answer. Is that, yeah, that's just a speed. Okay, we were asked to find a speed, and that's fine because, again, we've actually found that the mod of v is definitely 3.2 because, again, at the beginning, I assumed p is going to the right. It could have been going to the left, in which case both objects would be moving left at the end. So we don't actually know the velocity. We don't know if it's 3.2 or minus 3.2, but we know the mod of it, it's 3.2. Okay. And then let's look at part B. So part B sounds a bit, well, if you don't know what to do, then it sounds a bit confusing, but it's actually not too difficult. You just need to interpret correctly what it's asking. So it says, part B, find the magnitude of the impulse transmitted through the string. That's exactly the same thing as asking, what is the impulse on Q, or what is the impulse on P? It's going to be the same for both of them. So you can pick one, whichever one is easier, pick Q or pick P, and work out the impulse. And remember, impulse is change in momentum. Right, it's the change in little p momentum. So just find the change in momentum of either Q or P. And which one's easier? It will be Q, because Q was initially at rest, so therefore its initial momentum was 0. Right, it had a momentum of 0, and then its change in momentum is just what momentum did it end up getting. So in this case, let's write it formally, the impulse on Q, that's the change in momentum of Q. It's a bit confusing that I've written P there, because that means momentum P, not capital P. I'm going to try and do that as a lowercase. Okay, so that's a lowercase p, nothing to do with the capital P. Okay, so change momentum of Q, which is therefore mq times mv minus, oh sorry, not mv, hang on. So that's I'm thinking actually what would make sense here. I'm just going to not write this notation actually, it's too confusing with the P and the Q because I've confused myself with it. Let's just say the change in momentum of Q, because it's just too confusing the way I've written it there. So we've got mass of Q times V of Q minus U of Q, which is equal to 2 times, in this case, V of Q we figured out was just the V, U of Q is 0, so it's just 2V, so that's 2 times whatever we worked out earlier, which I think was 3.2, and you get 6.4. 6.4, is that right? Yeah. And remember, that's Newton seconds, right? That's what impulse is measured in. Change in momentum and impulse are Newton seconds. Okay, and then let's look at one final example. So in this question, we're given two objects. They are moving towards each other in opposite directions along the same straight line on a smooth horizontal surface, sort of the classic situation. However, in this case, you're given the initial speeds, but then instead of being given the final speed of one of the objects, you're just told the impulse due to the collision. So in other words, what the change in momentum is, and then find the velocity of A and velocity of B. So again, you just want to write out the notation formally. So see if you can do it yourself actually while I write it, and then see if we agree. So we've got mass of A equals 2, mass of B equals 4. The speeds of A and B are 3 and 2 meters per second respectively. They are going towards each other. So without loss of generality, let's say A is going to the right, and I'm also going to take right as positive. So then U of A is equal to 3, but U of B equals minus 2. And the impulse due to collision, the magnitude of the impulse, remember magnitude is 7. And when we say magnitude of I, what we're really saying is the magnitude of the impulse on A, and also that's the same thing as the impulse on B. Those are both equal to 7. Okay. So then let's write that formally. So the impulse of A is equal to the mass of A times V of A, which is what we're trying to find, minus U of A. Now, unfortunately, that left-hand side there is I of A rather than mod, right? Not magnitude. But actually, if you think about it, because we've, without less of generality, we've defined A as going to the right. Let's for a moment then see what the impulse must be. So that is to say, A is moving right, and therefore if it's going to collide with B, B is going to be moving left. So then they hit each other. So what direction is the impulse going to be? It's going to be in the opposite direction to the direction of motion. So if A is going right, its impulse is going to be going left. So that tells me that this is minus 7 in this case, without loss of generality. We've got minus 7 times 2, and then V of A we still don't know, but U of A we know is 3. And likewise, the impulse of B is its mass, the impulse on B is its mass multiplied by its final velocity minus its initial velocity. And that in this case is going to be 7, right? Because those two impulses are going to cancel each other out. Or alternatively, you can think of it as B is going left, but then when it receives an impulse, it receives an impulse going to the right, which is the positive direction. So we've got 4 times my unknown VB minus 2. Minus 2, so plus 2. Okay, so then let's just simplify those two. Unfortunately, it's a little bit slow doing it with the pen. In fact, let me just pause and write those answers down. Okay, so there are your answers. VA minus a half, VB minus a quarter. And I just want to now, I think this is a real point of confusion here, because it's also slightly not in disagreement with the textbook, but my way of thinking about it is perhaps slightly different. And it's all about this idea of the direction, right? Because if it's all about speeds, it's easy enough. But when you're talking about velocity, the direction matters. In the textbook, rather than calling it without loss of generality, assume it's this, the textbook phrases it as guess what direction they're going to go in, and then based on the answer you get, either your guess was right or your guess was wrong, in which case you flip the sign. But I'm not sure if I like that method, because really I think it's just a way of simplifying this concept of without less loss of generality. So I think it's better to instead remind yourself, it's a good idea to write, W log without loss of generality, to remind yourself that you are making an assumption so that you don't forget at the end, and then just interpret your results in light of that assumption. So in this case, we said A started off going right, and I should complete that picture really by saying B is therefore going left. And then without loss of generality, we assume this, and we ended up getting that VA is minus a half. So did it change direction, or did it stay in the same direction? It changed, right? So A changed. Let's make a note of that here for part A. A changed direction. And for B, it started going to the left in our assumption. It was negative direction. And we still get minus a quarter. So it didn't change direction, right? So same direction, right, for the case of B. And that's it really. I think that's simple enough to just stick with it that way. If you had done it the other way around, B going right and A going left, you would just end up with different numbers, but you'd still, not different numbers, sorry, but different signs, potentially, but the interpretation would still end up being the same. Either it changed direction or it was in the same direction. And the numbers themselves will be the same. So we've got a half, change direction, speed a half for A, and for B it's changed, it's same direction but speed of a quarter. Okay, I think this question is a little bit tricky, partly because it says velocity, and really a velocity is a speed along with a defined direction, left, right, up, down, north, east, or an angle. Technically, we can't fully answer that. I still don't know which things are going left and which things are going right in this scenario. The only thing I can do is describe the direction in relative terms compared to how things started. So all I can say is A, it's changed direction, but I can't say if it started left and went right or started right and went left. Okay, and this is a really tricky thing about some of these problems sometimes. I think even phrasing it as velocity is a bit of a cheat, because we don't really know the velocity, because I don't really know what direction it's going in. I don't know if it's going left or right. So just be wary of that. If you don't actually know the direction, sometimes it's fine to say it changed direction or it's in the same direction. Okay, I think that's probably the trickiest part of this chapter really, is just to not get confused with the signs. You want to be able to, personally I think it's nice to be able to just follow through with the notation without having to think about the real world scenario that much, and be confident that you're using the notation correctly. And a big part of that is getting the signs correct. And you're going to get the signs correct as long as you're careful about how you make your assumptions and how you make a note of these in your working. Okay. You always assume a positive direction, and perhaps you may even assume within a collision which way things initially start. Okay. Cool. Right, so I'm going to give you some time to do some questions yourself. This is page 1 of 2. Have a go at the question. And yeah, just pause the video now. And then you've got page 2, a couple more to try. If you're low on time, always a good idea to try the challenge one. Better to practice the harder stuff than the easier stuff, but ideally you might be able to finish all of it. Give it a go. You can pause the video now.